Tonight, we're going to talk about something that is quietly shaking the foundations of modern cosmology. There are two ways to measure how fast the universe is expanding. One looks at the oldest light in existence, the afterglow of the Big Bang itself. The other uses stars and explosions we can observe in the nearby universe. Both methods are extraordinarily precise. Both have been checked and rechecked by independent teams using different instruments over decades. And they don't agree. The numbers they produce are different, and the gap between them has only grown wider as our measurements have improved. This isn't a small technical glitch. If both answers are correct, then something about our understanding of the universe is wrong. And no one knows what it is. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems obvious but actually isn't obvious at all. The universe is expanding. You've probably heard that statement before. It gets repeated constantly in documentaries, in textbooks, in conversations about space. The universe is expanding. But what does that actually mean? Because when most people hear that the universe is expanding, they picture something like an explosion. They imagine galaxies flying outward through space like shrapnel from a bomb, shooting away from some central point where the Big Bang happened. That's a natural image, but it's completely wrong. Galaxies aren't moving through space away from some center. Space itself is stretching. And this distinction matters enormously, because once you understand what expansion really means, you begin to see why measuring it has become one of the most important and most frustrating challenges in all of science. Think of it this way. Imagine you have a balloon. Not blown up yet, just a flat, deflated balloon. Now imagine you draw dots on the surface of that balloon with a marker. Each dot represents a galaxy. Now start blowing the balloon up. As the rubber stretches, something interesting happens. Every dot moves away from every other dot. Not because the dots themselves are sliding across the rubber, but because the rubber between them is expanding. If you were a tiny creature living on one of those dots, you'd look around and see every other dot receding from you. You might think you were at the center of the expansion, but you wouldn't be. There is no center. Every dot sees every other dot moving away. The expansion is happening everywhere, in the fabric of the balloon itself. The universe works the same way. Space is the balloon. Galaxies are the dots. And the expansion isn't galaxies moving through space. It's space itself stretching, creating more distance between things that aren't held together by local forces like gravity. The Earth isn't getting farther from the Sun because the gravity of the solar system holds everything together. Our galaxy isn't flying apart because gravity holds the stars in their orbits. Even our local group of galaxies is gravitationally bound. But on the larger scales, between galaxy clusters separated by hundreds of millions or billions of light years, space is stretching. And the farther apart two objects are, the faster the space between them grows. This means distant galaxies are receding from us. Not because they're racing away through space, but because the space between us and them is continuously being created. It's a subtle but profound difference. In an explosion, things fly outward from a point. In the expansion of the universe, there is no center. Every point in space sees every other sufficiently distant point moving away. The expansion is a property of space itself, not a movement of objects through space. Now, how do we know this? How did scientists figure out that the universe is expanding in the first place? The answer begins with light, and specifically with what happens to light when the source of that light is moving away from you. You're probably familiar with the Doppler effect for sound. When an ambulance drives toward you, its siren sounds higher pitched. When it drives away, the pitch drops. This happens because the motion of the ambulance compresses the sound waves in front of it, making them shorter and higher pitched, and stretches the sound waves behind it, making them longer and lower pitched. Light behaves similarly. When a source of light is moving toward you, the light waves get compressed. They shift toward the blue end of the spectrum, shorter wavelengths. When a source of light is moving away from you, the light waves get stretched. They shift toward the red end of the spectrum, longer wavelengths. Astronomers call this redshift. And in the case of the expanding universe, it's not exactly the same as the Doppler effect, because the galaxies aren't moving through space. Instead, the light itself is being stretched as it travels through expanding space. The wavelength of the light gets longer because the space the light is traveling through is getting longer. The effect is similar though. Light from distant galaxies arrives at our telescopes with its wavelengths stretched, shifted toward the red end of the spectrum. And the farther away a galaxy is, the more its light is redshifted. This is how we measure recession velocity. We look at the light from a distant galaxy, measure how much its spectral lines have shifted toward longer wavelengths, and from that shift, we calculate how fast the galaxy appears to be moving away from us. In the late 1920s, an astronomer named Edwin Hubble made observations that would change our understanding of the universe forever. Hubble was working at the Mount Wilson Observatory near Los Angeles, using what was then the most powerful telescope in the world, the 100-inch Hooker telescope. He was studying galaxies, which at the time were still being debated. Many astronomers thought these fuzzy patches of light were just nebulae within our own Milky Way. Hubble helped settle this debate by measuring the distances to several of these objects and showing they were far too distant to be inside the Milky Way. They were separate galaxies, island universes in their own right, millions of light years away. But Hubble did something even more important than proving galaxies existed beyond our own. He combined his distance measurements with redshift measurements, many of which had been compiled by another astronomer named Vesto Slipher, who had spent years carefully measuring the redshifts of dozens of galaxies. When Hubble plotted galaxy distance against recession velocity, he found something astonishing. There was a clear pattern. The farther away a galaxy was, the faster it was receding from us. This relationship was remarkably consistent. A galaxy twice as far away was receding roughly twice as fast. A galaxy 3 times as far away was receding roughly 3 times as fast. This was a straight line on a graph. A simple, clean, proportional relationship between distance and velocity. This discovery, published in 1929, is one of the most important in the history of science. It showed that the universe is expanding, not just in one direction, not just in some places, everywhere. The entire fabric of space is stretching, carrying galaxies with it. And the relationship Hubble found, the proportionality between distance and recession velocity, became known as Hubble's law. Now, here's the critical part. If the relationship between distance and velocity is proportional, then you can describe it with a single number. That number is the slope of the line on the graph. It tells you how much faster a galaxy is receding for every additional unit of distance. This number is called the Hubble constant, and it's usually written as h0. It's measured in a unit that sounds complicated, but is actually quite intuitive. Kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light years. It's the standard unit astronomers use for intergalactic distances. So when we say the Hubble constant is, for example, 70 kilometers per second per megaparsec, what we mean is this. For every megaparsec of distance between us and a galaxy, that galaxy is receding from us an additional 70 kilometers per second. A galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. The relationship is clean and proportional, and the Hubble constant is the number that defines that proportionality. This might sound like just another number in physics, another constant to memorize alongside the speed of light or the gravitational constant. But the Hubble constant is far more important than it might appear. It's not just telling us how fast the universe is expanding right now. It's connected to almost everything else in cosmology. It tells us the age of the universe. If you know how fast things are moving apart, you can work backward and figure out when everything was in the same place. A higher Hubble constant means the universe is expanding faster, which means it took less time to reach its current size, which means the universe is younger. A lower Hubble constant means a slower expansion, which means the universe is older. The age of the universe depends directly on this one number. It also tells us the size of the observable universe, because the expansion rate determines how far light has been able to travel since the Big Bang, accounting for the stretching of space along the way. It affects our understanding of dark energy, the mysterious force accelerating the expansion. It influences our models of how galaxies formed, how matter clumped together in the early universe, and how the large-scale structure of the cosmos evolved over billions of years. Getting the Hubble constant right isn't just a nice thing to do. It's essential. Every model of the universe, every prediction about its past and future, every calculation about its contents and structure depends on this one number. If we get it wrong, everything built on top of it could be wrong too. It's the foundation on which modern cosmology is constructed. When Hubble first estimated this constant in 1929, he got a value of about 500 kilometers per second per megaparsec. That's enormously high compared to what we know today. If that value were correct, the universe would be only about 2 billion years old. But even in the 1930s, geologists already knew that some rocks on Earth were older than 2 billion years. And astronomers knew that some stars appeared to be older than that too. So there was an immediate problem. The universe couldn't be younger than the things inside it. Something was wrong. The issue turned out to be Hubble's distance measurements. Measuring distances in space is extraordinarily difficult. You can't just point a laser at a galaxy and wait for the beam to bounce back. Galaxies are millions or billions of light years away. Light itself takes millions of years to cross those distances. Instead, astronomers have to use indirect methods, building up a chain of distance measurements that starts with nearby objects and extends step by step to more distant ones. This chain is called the cosmic distance ladder. In Hubble's time, the distance ladder was crude and poorly calibrated. His distance estimates for galaxies were systematically too small, which made it look like those galaxies were closer than they actually were. If you think a galaxy is closer than it really is, but you measure its recession velocity correctly, then you overestimate the Hubble constant. You think the expansion rate is higher than it actually is. Over the following decades, astronomers improved their distance measurements, and the Hubble constant dropped. By the 1950s, it had fallen to around 180. By the 1970s, it was somewhere between 50 and 100. But here's where things got messy, and where the seeds of our current crisis were planted. During the 1970s, 80s, and 90s, two camps of astronomers were measuring the Hubble constant and getting very different answers. One group, led by astronomer Alan Sandage, consistently found values around 50 to 55. Another group, led by astronomer Gérard de Vaucouleurs, found values around 90 to 100. The disagreement was enormous. A Hubble constant of 50 means the universe is about 13 billion years old. A Hubble constant of 100 means the universe is only about 6 or 7 billion years old. These aren't minor differences. They imply fundamentally different universes with different ages, different sizes, and different histories. The debate raged for decades. Each side accused the other of systematic errors in their distance measurements. Each side refined their techniques, checked and rechecked their data, and published paper after paper defending their position. It was one of the most contentious debates in modern astronomy. And the core of the problem was the same thing that had plagued Hubble originally. Measuring distances in space is incredibly difficult. Small errors in distance measurement translate directly into errors in the Hubble constant, and those errors cascade through every other cosmological calculation. In the mid-1990s, NASA launched a space telescope specifically to resolve this debate. The Hubble Space Telescope, named after Edwin Hubble himself, had many scientific goals, but one of its primary missions was to pin down the Hubble constant to within 10% accuracy. A dedicated team called the Hubble Key Project spent years using the Space Telescope to observe Cepheid variable stars in distant galaxies. Cepheid variables are a specific type of star that brightens and dims in a regular pattern. The period of this pulsation, how long it takes to go from bright to dim and back again, is directly related to the star's intrinsic luminosity, meaning how much light it actually produces. By measuring the period, you know the luminosity. By comparing the luminosity to how bright the star appears from Earth, you can calculate the distance. Cepheids are one of the most reliable rungs on the cosmic distance ladder, and observing them with the Hubble Space Telescope, which sits above Earth's atmosphere and can see much more clearly than ground-based telescopes, was a major advance. In 2001, the Hubble Key Project published its final result. The Hubble constant, they reported, was 72 kilometers per second per megaparsec, with an uncertainty of about 10%. This was roughly in the middle of the range that the two competing groups had been arguing about. Neither side was exactly right. The answer fell between them. The result seemed to settle the debate. A Hubble constant of about 70 implied a universe about 13.8 billion years old, consistent with other evidence. The scientific community largely accepted this value and moved on to other questions. For a brief period, cosmologists felt like the big questions had been answered. The universe was about 13.8 billion years old, made of about 5% ordinary matter, about 27% dark matter, and about 68% dark energy. This model, called the lambda CDM model, fit almost all the observations beautifully. It was elegant, consistent, and predictive. It became the standard model of cosmology. Textbooks were written, courses were taught, conferences were held. The basic picture of the universe seemed settled, but it wasn't settled. Not really. Because while the Hubble Space Telescope was refining its measurement from the nearby universe, a completely different approach to measuring the Hubble constant was being developed. This approach didn't use stars or supernovae or anything in the nearby universe at all. Instead, it looked at the oldest light in existence, light that had been traveling for over 13 billion years, light that carried information about the universe as it was just a few 100,000 years after the Big Bang. And when scientists analyzed that ancient light and used it to calculate what the Hubble constant should be, they got a different number. Not wildly different. Not different by a factor of 2 or 3 like in the old Sandage versus de Vaucouleurs debate, but different enough to be troubling. Different enough that as measurements improved, as error bars got smaller, the two numbers refused to converge. They kept sitting apart, stubbornly, persistently, with a gap that wouldn't close no matter how carefully anyone measured. This is where our story really begins. Because the gap between these two numbers, between the expansion rate measured from the nearby universe and the expansion rate predicted from the ancient universe, has become one of the biggest unsolved problems in modern physics. It's called the Hubble tension. And it might be telling us that something fundamental about our understanding of the cosmos is incomplete. Understanding why this tension matters requires appreciating something about how science normally works. When two different methods measure the same thing and get different answers, the first assumption is always that somebody made a mistake. Maybe one measurement has a systematic error, some unnoticed bias that's pushing the result in one direction. Maybe the instruments aren't calibrated correctly. Maybe the analysis has a flaw. This is the mundane explanation, and it's usually the right one. Most disagreements in science get resolved when someone finds the error. But the Hubble tension has resisted this explanation. Both measurements have been refined, improved, and cross-checked by multiple independent teams using different instruments and different techniques. The error bars have gotten smaller and smaller over the years, and the gap hasn't closed. It has, if anything, become more statistically significant as the measurements have improved. This is unusual. In most cases, better measurements resolve a disagreement. In this case, better measurements have made the disagreement sharper. To understand the significance of this, you need to appreciate what the Hubble constant really represents physically. It isn't just a description of how things are moving right now. It encodes the entire expansion history of the universe. The current expansion rate is the result of everything that has happened since the Big Bang. The initial conditions of the universe, the amount of matter it contains, the amount of radiation, the amount of dark energy, the curvature of space, the interaction between all these components over 13.8 billion years of cosmic evolution. All of this feeds into the expansion rate we measure today. So when two methods disagree about the expansion rate, they're not just disagreeing about one number. They're potentially disagreeing about the fundamental contents and dynamics of the universe itself. Either one of the measurements is wrong, or our model of the universe, the model that connects the early universe to the late universe, is missing something. And missing something in a cosmological model isn't a small thing. It would mean that our best understanding of how the universe works, the model that has been tested and confirmed by dozens of independent observations over decades, has a gap. Not a minor gap. A gap significant enough to produce a measurable discrepancy in one of the most fundamental quantities in all of cosmology. That's why the Hubble tension is so important. It isn't just about a number. It's about whether our entire framework for understanding the universe is complete. The expansion rate is woven into everything. If we're getting it wrong, if two equally valid methods are giving us different answers, then something somewhere in our picture of reality needs to be revised. And nobody yet knows what that something is. What makes this even more unsettling is how fundamental the expansion of the universe is to everything else we know. The expansion isn't just one feature of the universe among many, it's the defining characteristic of the cosmos we live in. Every observation we make of distant objects is affected by it. Every calculation of cosmic distances relies on it. Every model of how galaxies formed, how elements were created in the first few minutes after the Big Bang, how the cosmic microwave background radiation was produced, all of it assumes a particular expansion history. If that history is different from what we think, even slightly, the consequences ripple through everything. The age of the universe would change. The distances to faraway galaxies would change. The amount of dark energy we infer would change. The conditions in the early universe that gave rise to the first atoms, the first stars, the first galaxies, all of those might need to be recalculated. The expansion of the universe isn't a detail. It's the framework. And right now, that framework has a crack in it. A small crack, maybe. A crack that might turn out to have a boring explanation. But also a crack that might be the first sign of something genuinely new. Something that could force us to rethink what we thought we knew about the cosmos. The universe is expanding. We know that. But how fast it's expanding depends on who you ask and how they measure it. And that disagreement, that tension, might be the single most revealing crack in our picture of the cosmos right now. For most of the 20th century, astronomers assumed the debate about the Hubble constant was simply a measurement problem. Build better telescopes, develop better techniques, reduce the error bars. Eventually, the true value would emerge and everyone would agree. That assumption seemed reasonable. Science advances through better measurement. Every generation builds better instruments and sees more clearly than the last. The history of the Hubble constant supported this expectation. It started absurdly high at 500, dropped over the decades as measurements improved, and by the early 2000s seemed to have settled around 70 to 75. The expectation was that as measurements continued to improve, the uncertainty would shrink and a single consensus value would crystallize. What nobody expected was that as measurements improved, a new disagreement would emerge. Not between sloppy measurements and careful ones, not between old instruments and new ones, but between two fundamentally different approaches to measuring the same number, each carried out with extraordinary care, each using the most powerful instruments available, and each giving a different answer. The universe is trying to tell us something. The question is whether we're ready to hear it. So, how do you actually measure how fast the universe is expanding? It sounds like it should be straightforward. You look at distant galaxies, you figure out how far away they are, you measure how fast they're moving away from you, and you calculate the ratio. Distance divided into velocity gives you the Hubble constant. Simple, right? It's not simple. It's one of the hardest measurements in all of science. And the difficulty comes almost entirely from one side of the equation. Velocity is actually the easy part. Measuring how fast a galaxy is receding from us is relatively straightforward. You look at the light from that galaxy, you identify spectral lines, the fingerprints of specific elements like hydrogen or calcium, and you measure how much those lines have been shifted toward the red end of the spectrum. The amount of redshift tells you the recession velocity directly. Astronomers have been doing this for over a century and they're very good at it. The precision is excellent. Recession velocity is not where the problem lies. The problem is distance. Measuring distances in space is brutally, almost impossibly difficult. You can't send out a tape measure. You can't bounce a signal off a galaxy and time how long it takes to return. Galaxies are millions or billions of light years away. The light you're seeing from them left millions or billions of years ago. There's no direct way to reach out and touch them, no way to measure the gap between here and there in any straightforward physical sense. Instead, astronomers have to be clever. They have to use indirect methods, building up a chain of measurements that starts with things that are close and well understood and extends step by step to things that are far away and harder to see. This chain is called the cosmic distance ladder. And it is, without exaggeration, one of the greatest achievements in the history of science. It's also the source of one side of the Hubble tension. Understanding how it works is essential to understanding why two measurements of the same universe can produce different answers. The first rung of the cosmic distance ladder is the most direct and the most reliable. It's called parallax, and it's based on a simple geometric principle that you can demonstrate right now without any equipment at all. Hold your finger up in front of your face at arm's length. Close your left eye and look at your finger with just your right eye. Now switch. Close your right eye and look with just your left. Your finger appears to jump back and forth against the background. This apparent shift is parallax. The reason your finger appears to move is that your two eyes are looking at it from slightly different positions. They're separated by a few inches, and that separation creates two slightly different lines of sight. By measuring how much your finger appears to shift and knowing the distance between your eyes, you can calculate how far away your finger is using basic trigonometry. Astronomers use exactly the same principle, but instead of two eyes separated by a few inches, they use two positions of the Earth, separated by the diameter of its orbit around the Sun. In January, the Earth is on one side of its orbit. In July, 6 months later, it's on the opposite side. The distance between these two positions is about 300 million kilometers, or 2 astronomical units. That's a very long baseline. When astronomers photograph a relatively nearby star in January and then again in July, that star appears to shift slightly against the background of much more distant stars. The amount of this shift, measured in tiny fractions of a degree called arc seconds, tells you the distance to the star. The smaller the shift, the farther away the star is. Stars that are closer shift more. Stars that are farther shift less. The mathematics is clean and the principle is simple, but parallax has a fundamental limitation. It only works for relatively nearby stars. As stars get farther away, the apparent shift gets smaller and smaller. Eventually, it becomes so tiny that it's impossible to measure accurately, even with the best instruments. From the ground, parallax is useful out to only a few hundred light years. Space-based missions like Hipparcos, launched in 1989, extended this to a few thousand light years. The Gaia spacecraft, launched by the European Space Agency in 2013, has pushed parallax measurements to tens of thousands of light years with extraordinary precision, mapping the positions and distances of over 1 billion stars in the Milky Way. Gaia has been transformative for many areas of astronomy, and its parallax measurements provide the absolute foundation for the distance ladder. But even Gaia can't measure parallax for stars in other galaxies. Other galaxies are millions of light years away. The parallax shift of a star in another galaxy would be so infinitesimally small that no instrument we have or could conceivably build would be able to detect it. So parallax alone can't tell us the distances to galaxies. It can only anchor the very first rung of the ladder. To go farther, we need something else. This is where Cepheid variable stars come in. Cepheids are one of the most important tools in all of astronomy, and they form the second rung of the cosmic distance ladder. A Cepheid is a type of star that pulsates. It rhythmically brightens and dims over a period that can range from a day or two to over 100 days. The star physically swells and contracts, growing larger and brighter, then smaller and dimmer, in a regular cycle that repeats over and over. What makes Cepheid so valuable is a remarkable relationship discovered in 1912 by an astronomer named Henrietta Swan Leavitt. Leavitt was studying Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere. She noticed something extraordinary. The Cepheids that took longer to complete one pulsation cycle were brighter than the ones that pulsed more quickly. There was a tight, reliable relationship between the period of pulsation and the intrinsic luminosity of the star. A Cepheid with a period of 10 days had a specific luminosity. A Cepheid with a period of 30 days was brighter by a predictable amount. A Cepheid with a period of 50 days was brighter still. The relationship was clean and consistent. This period luminosity relationship, now called the Leavitt law, is one of the most important discoveries in the history of astronomy. It turned Cepheid variables into what astronomers call standard candles. If you can measure a Cepheid's pulsation period, which is easy to do, you just watch the star over time and measure how long each cycle takes, then you know its intrinsic luminosity. And if you know how bright a star actually is, and you measure how bright it appears from Earth, the difference tells you the distance. A candle that appears dim might be dim because it's intrinsically faint, or it might be dim because it's very far away. But if you know it's intrinsically bright and it still appears faint, it must be far away. The mathematics relating apparent brightness, intrinsic brightness, and distance is well established. Light dims with the square of the distance, a relationship known as the inverse square law. Double the distance and the brightness drops to 1/4. Triple the distance, and it drops to 1/9. This allows you to calculate distances with considerable precision. Cepheids can be observed in galaxies up to about 100 million light years away using the Hubble Space Telescope and the James Webb Space Telescope. That's an impressive reach. It takes us far beyond the Milky Way, deep into the realm of other galaxies. Edwin Hubble himself used Cepheids to prove that Andromeda was a separate galaxy and to make his first measurements of the expansion rate. Cepheids remain one of the most trusted distance indicators in astronomy today, but 100 million light years isn't far enough to measure the Hubble constant accurately. To do that, you need to measure distances to galaxies that are receding fast enough that their velocity is dominated by the expansion of the universe rather than by local gravitational motions. Galaxies within about 100 million light years of us are affected by the gravitational pull of nearby galaxy clusters and superclusters. They have peculiar velocities, meaning they move in response to local gravity in addition to the overall cosmic expansion. These local motions contaminate the signal. To get a clean measurement of the expansion rate, you need to observe galaxies that are several hundred million light years away or farther, where the expansion signal overwhelms the local gravitational noise. Cepheids can't reach that far, so we need a third rung on the ladder, something brighter than Cepheids, something that can be seen across much greater distances, something that can serve as a standard candle at cosmological distances. That something is a Type 1a supernova. A Type 1a supernova is a specific kind of stellar explosion. It occurs in a binary star system where one of the stars is a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. The white dwarf accumulates matter from its companion star. As matter piles onto the white dwarf, its mass increases. When the mass reaches a critical threshold, about 1.4 times the mass of our Sun, a value called the Chandrasekhar limit, the white dwarf can no longer support itself against gravitational collapse. Carbon fusion ignites throughout the star almost simultaneously, and the entire white dwarf is destroyed in a thermonuclear explosion of extraordinary violence. The explosion is so bright that a single Type 1a supernova can outshine its entire host galaxy for weeks. It's visible across billions of light years of space. What makes Type 1a supernovae useful as distance indicators is that they all explode at roughly the same mass, the Chandrasekhar limit. Because they start from similar conditions, the explosions produce roughly similar peak luminosities. They're not perfectly identical, but astronomers have developed techniques to standardize them. By measuring the shape of the light curve, specifically how quickly the supernova brightens and then fades, astronomers can determine its intrinsic brightness with impressive precision. A supernova that fades slowly is intrinsically brighter. One that fades quickly is intrinsically dimmer. Once you know the intrinsic brightness and measure the apparent brightness, you can calculate the distance, just as with Cepheids. The difference is that supernovae are enormously brighter than Cepheids. They can be observed at distances of billions of light years, far beyond where Cepheids fade from view. Here's how the whole distance ladder works as an integrated system. First, you use parallax to measure distances to nearby Cepheids within the Milky Way. Gaia has been essential for this step, providing precise parallax distances to hundreds of Cepheids. This calibrates the Cepheid period luminosity relationship. You know the exact distance to these nearby Cepheids from parallax. You know their periods, and you know their apparent brightness. So you can determine their intrinsic brightness. This calibration anchors the whole system. Next, you find Cepheids in galaxies that have also hosted Type 1a supernovae. You use the calibrated Cepheid relationship to determine the distance to these host galaxies. Now, you know the distance to the supernovae in those galaxies. You know the distance and the apparent brightness of each supernova, so you can determine its intrinsic brightness. This calibrates the supernova brightness, creating a standardized relationship between light curve shape and luminosity. Finally, you observe Type 1a supernovae in very distant galaxies, far beyond where Cepheids can be seen. You use the calibrated supernova relationship to determine the distances to these distant galaxies. You combine these distances with the galaxy's recession velocities measured from their redshifts. And from the relationship between distance and velocity, you calculate the Hubble constant. Each rung of the ladder depends on the one below it. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae reach into the deep universe where the expansion signal is cleanest. It's an elegant system, built over decades by hundreds of astronomers using the most powerful telescopes ever constructed. But it's also fragile. Any error in the lower rungs propagates upward. If the parallax distances to nearby Cepheids are slightly off, the Cepheid calibration is wrong. If the Cepheid calibration is wrong, the supernova calibration is wrong. If the supernova calibration is wrong, the final Hubble constant is wrong. Every step has to be right, or the whole chain falls apart. The team that has pushed this approach to its highest precision is the SH0ES project, led by Nobel laureate Adam Rees at Johns Hopkins University. SH0ES stands for supernova H0 for the equation of state, and for over 2 decades the team has been refining every rung of the distance ladder with painstaking care. They've used the Hubble Space Telescope to observe Cepheids in dozens of galaxies that have hosted Type 1a supernovae. They've cross-checked their Cepheid calibration using multiple independent geometric distance anchors, including parallax from Gaia, eclipsing binary stars in the Large Magellanic Cloud, and the water megamaser in the galaxy NGC4 258. Each of these provides an independent way to measure distance without relying on Cepheids, and they all give consistent results. The SH0ES team's latest measurement puts the Hubble constant at 73.04 kilometers per second per megaparsec, with an uncertainty of only about 1.4%. That's remarkably precise, and it's the number that sits on one side of the Hubble tension. But there's a completely different way to measure the Hubble constant, a way that doesn't use the distance ladder at all, a way that doesn't rely on stars or supernovae or anything in the nearby universe. Instead, it reaches back to the very beginning, to the oldest light in the cosmos, and uses that ancient signal to predict what the expansion rate should be today. This is the early universe approach, and it centers on something called the cosmic microwave background radiation. The cosmic microwave background, or CMB, is a faint glow of microwave radiation that fills every cubic centimeter of space in the universe. It comes from all directions equally, with almost perfect uniformity. If you could see in microwaves, the entire sky would glow with a nearly uniform light. This radiation isn't coming from any star or galaxy. It's coming from the universe itself, from a specific moment in cosmic history about 380,000 years after the Big Bang. In the very early universe, everything was extraordinarily hot and dense. Matter and radiation were so tightly coupled that the universe was essentially opaque. Photons, the particles of light, couldn't travel any significant distance before being scattered by free electrons. The universe was like a dense fog. Light couldn't get through. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin. At this point, something critical happened. The universe cooled enough for electrons to combine with atomic nuclei to form neutral atoms, mostly hydrogen and helium. This process is called recombination. Once the electrons were bound into atoms, photons could suddenly travel freely. The fog cleared. Light was released. The photons that were emitted at that moment, from every point in the universe simultaneously, have been traveling through space ever since. Over 13.8 billion years, the expansion of the universe has stretched their wavelengths enormously. What started as visible and infrared light has been redshifted all the way into the microwave part of the spectrum. This is the cosmic microwave background. It's the afterglow of the Big Bang, a snapshot of the universe as it was when it was only 380,000 years old. The CMB was predicted in the late 1940s by Ralph Alpher and Robert Herman, who calculated that the early universe should have produced a bath of radiation that would still be detectable today, cooled to a temperature of a few degrees above absolute zero. It was accidentally discovered in 1965 by Arno Penzias and Robert Wilson at Bell Labs in New Jersey. They were testing a sensitive microwave antenna and kept picking up a persistent background noise that they couldn't eliminate. It came from every direction. It didn't vary with the time of day or the season. It wasn't coming from the Earth or the Sun or the Milky Way. After much confusion, they realized they were detecting the cosmic microwave background, the ancient light of the Big Bang itself. They won the Nobel Prize for this discovery. The CMB has a temperature of about 2.725 degrees Kelvin, meaning 2.725 degrees above absolute zero. It's almost perfectly uniform across the sky, but not quite perfectly uniform. There are tiny fluctuations, variations of about 1 part in 100,000. Some spots are very slightly warmer, others are very slightly cooler. These fluctuations are incredibly important because they represent the seeds of all the structure we see in the universe today. The slightly denser regions in the early universe, the regions that were just a tiny bit warmer and denser than average, eventually attracted more matter through gravity and grew into the galaxies, galaxy clusters, and superclusters we observe today. The pattern of these fluctuations is not random. It has a very specific statistical structure that depends on the physical conditions in the early universe. The pattern depends on how much ordinary matter the early universe contained, how much dark matter, how much radiation, how fast the universe was expanding at that time, and the geometry of space itself. By measuring the pattern of fluctuations in the CMB with high precision, you can determine all of these cosmological parameters, including, crucially, the expansion rate. The most precise measurement of the CMB ever made came from the Planck satellite, a European Space Agency mission that operated from 2009 to 2013. Planck mapped the entire sky in microwave frequencies with extraordinary precision, measuring the temperature of the CMB at millions of points with an accuracy of millionths of a degree. The resulting map is one of the most important datasets in all of science. From this map, scientists extracted the pattern of hot and cold spots and analyzed their statistical properties. They measured what's called the power spectrum of the CMB, which describes how much variation exists at different angular scales. Large spots, small spots, the relative amplitudes of these features, all of it encodes information about the early universe. The power spectrum has a series of peaks, specific angular scales where the fluctuations are strongest. These peaks arise from sound waves that were traveling through the early universe before recombination. Yes, sound waves. In the dense plasma of the early universe, matter and radiation were coupled together, and density fluctuations propagated through this plasma as acoustic waves, similar to sound waves in air, but traveling at about half the speed of light, through a medium of unimaginable density. The positions, heights, and spacing of these peaks in the power spectrum tell you about the composition and geometry of the universe, with remarkable precision. Scientists take this data and feed it into the lambda CDM model, the standard model of cosmology. This model describes the universe as containing ordinary matter, dark energy, and radiation, with a specific set of initial conditions and a specific geometry. By adjusting the parameters of the model until it best fits the observed B power spectrum, scientists can determine the cosmological parameters with extraordinary precision. The Planck results, published in their final form in 2018, give a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. This is an incredibly precise measurement, but it's not a direct measurement of the current expansion rate in the way the distance ladder provides. It's a prediction. The Planck team measured the conditions in the early universe and used the standard cosmological model to evolve those conditions forward in time, predicting what the expansion rate should be today if the model is correct, and if nothing unexpected happened between then and now. That distinction is critical. The distance ladder measures the expansion rate directly, using observations of objects in the relatively nearby universe. The CMB approach infers the expansion rate indirectly, using observations of the early universe combined with a theoretical model. Both approaches are rigorous, sophisticated, and carried out by world-class scientists. Both have been subjected to extensive internal checks and cross-validation. Both have small, well-characterized uncertainties, and they give different answers. 73 from the distance ladder, 67.4 from the CMB, a difference of about 5 to 6 kilometers per second per megaparsec. That might not sound like much in absolute terms, but given the precision of both measurements, it's enormous in the statistical terms. The error bars don't overlap. The gap is real, persistent, and has grown more significant as both methods have improved. What makes this situation so remarkable is that neither measurement is easy to dismiss. The distance ladder approach has been cross-checked using multiple independent calibration anchors. The Cepheid observations have been verified by different telescopes and different teams. The Type 1a supernova data has been collected by multiple surveys using different instruments. Every potential source of systematic error that anyone has thought of has been investigated, tested, and either ruled out or corrected for. The measurement keeps coming back to about 73. The CMB approach has been equally thoroughly tested. The Planck satellite's data has been analyzed by multiple independent groups using different analysis pipelines. The results are consistent with earlier CMB experiments like WMAP, which operated from 2001 to 2010. The lambda CDM model that's used to interpret the data fits the CMB power spectrum with extraordinary precision, matching the observed peaks and troughs with an accuracy that's almost eerie. The model works beautifully. The measurement keeps coming back to about 67.4. Two methods, two numbers, both precise, both well tested, both internally consistent. And they disagree. This is the Hubble tension. And it's not going away. It's one of the most important open problems in cosmology, and its resolution, whatever form that takes, could reshape our understanding of the universe. Either one of the measurements has an error that nobody has been able to find despite decades of searching, or the model connecting the early universe to the late universe is incomplete, or something happened between the era of the CMB and today that our current physics doesn't account for. Each of these possibilities has profound implications, and none of them has been confirmed. What makes this tension particularly tantalizing is the way the two measurements approach the same question from opposite directions. The distance ladder starts here and now, in the present-day universe, and looks outward at objects we can observe directly. It measures what the expansion rate actually is, right now, in the universe as it exists today. The CMB starts at the beginning, 380,000 years after the Big Bang, and works forward using the best theoretical model we have, predicting what the expansion rate should be based on the conditions that existed at the dawn of time. One measurement looks at the universe as it is, the other looks at the universe as it was and predicts what it should have become. And the two answers are different. Something in the chain, some link connecting the early universe to the late universe, appears to be either broken or missing. The universe we observe today doesn't quite match the universe that our best model predicts from the initial conditions. Either our observations are subtly wrong, or our model is subtly incomplete. And either way, something fundamental about how we understand the cosmos needs to change. The beauty of the Hubble tension is that it's not a vague philosophical disagreement. It's a precise quantitative mismatch between two numbers that should agree and don't. It's the kind of discrepancy that physics thrives on, because discrepancies like this have historically been the doorways to new understanding. Throughout the history of physics, the biggest breakthroughs haven't come from expected results. They've come from the stubborn, uncomfortable moments when a prediction doesn't quite match an observation, and nobody can figure out why. Those moments feel like failures at first. They look like errors or oversights, but sometimes they turn out to be doorways into entirely new ways of understanding a reality. The Hubble tension has that same quality. It might turn out to have a mundane explanation, some subtle systematic error in one or both measurements that will eventually be found and corrected. But as the years pass and the measurements get better and the gap persists, the mundane explanation is becoming harder and harder to defend. And the exciting possibility that the universe is hinting at something genuinely new becomes more and more plausible. So now we have two numbers sitting side by side, and we need to understand why their disagreement is such a big deal. 73.04 from the distance ladder, 67.4 from the cosmic microwave background, a gap of about 5 to 6 kilometers per second per megaparsec. On the surface, that might seem like a small difference. After all, both numbers are in the same ballpark. They're both in the 60s or low 70s. They agree to within about 8%. In everyday life, if two people estimated the distance to a city and their answers were within 8% of each other, you'd say they basically agreed. You wouldn't call it a crisis. But cosmology isn't everyday life. And in science, whether a disagreement is significant depends not just on the size of the gap, but on the size of the uncertainty in each measurement. If both measurements had large error bars, if the distance ladder result was 73 plus or minus 10 and the CMB result was 67 plus or minus 10, then the two ranges would overlap easily. There would be no tension at all. Both measurements would be consistent with a true value somewhere around 70, and no one would lose any sleep over it. That's roughly where things stood in the early 2000s. The measurements disagreed somewhat, but the uncertainties were large enough that the disagreement could easily be chalked up to imprecise data. Nobody panicked. The expectation was that as instruments improved and error bars shrank, the two values would converge. But that's not what happened. What happened is that both measurements got dramatically more precise and the gap didn't close. The distance ladder measurement came down to 73.04 plus or minus 1.04. The CMB measurement settled at 67.4 plus or minus 0.5. Look at those error bars. They're tiny. The distance ladder team is claiming they know their number to within about 1.5%. The Planck team is claiming they know their number to within less than 1%. And the two ranges don't overlap. The distance ladder's lowest plausible value, about 72, is still well above the CMB's highest plausible value, about 68. There's a gap between the bottom of one measurement and the top of the other that neither can reach. This is what makes it a tension rather than just a disagreement. The measurements are too precise for the gap to be explained by simple statistical noise. Something real is going on. To understand just how significant this disagreement is, we need to talk about something called sigma. In statistics, sigma is a way of measuring how unlikely a result is to have occurred by chance. 1 sigma means there's roughly a 32% chance the result could be a random fluctuation. That's not very significant. It happens all the time. Results at 1 sigma are considered unremarkable. Nobody publishes a paper over a 1 sigma result. 2 sigma means there's roughly a 5% chance of a random fluctuation. That starts to get interesting, but it's still not convincing. Scientists see 2 sigma results regularly, and many of them turn out to be nothing when more data is collected. 3 sigma means there's roughly a 0.3% chance of a random fluctuation. That's about 1 in 350. At 3 sigma, scientists start paying serious attention. It's considered evidence that something real might be happening, though it's not yet definitive. Many 3 sigma results have evaporated with better data, so caution is warranted. 4 sigma means there's roughly a 1 in 16,000 chance of a random fluctuation. This is strong evidence. Very few 4 sigma results turn out to be statistical flukes. At this level, most scientists are fairly confident something real is going on, even if they might not be ready to call it a discovery. 5 sigma is the gold standard. It means there's roughly a 1 in 3.5 million chance that the result is a random fluctuation. When physicists at CERN announced the discovery of the Higgs boson in 2012, they required a 5 sigma result before making the claim. 5 sigma is the threshold that particle physics uses for declaring a discovery. It's the point at which the probability of a false alarm is so vanishingly small that the scientific community accepts the result as real. The Hubble tension, as of the most recent measurements, sits at roughly 4 to 6 sigma, depending on exactly which data, sets you compare, and how you handle certain statistical details. Most analyses put it at about 5 sigma. Let me say that again because it's important. The disagreement between the early universe and late universe measurements of the Hubble constant is at the 5 sigma level. That's the same threshold physicists use to declare a new fundamental particle has been discovered. If this were a particle physics experiment and you found a signal at 5 sigma, you'd be popping champagne and writing your Nobel Prize speech. In cosmology, the implications are potentially just as profound, though the situation is more complicated, because we're dealing with 2 complex measurement systems rather than a single controlled experiment. At 5 sigma, the probability that this disagreement is just a statistical fluke, just bad luck in the data, is about 1 in 3.5 million. That's vanishingly small. For practical purposes, we can rule out random chance as an explanation. Something real is causing the 2 methods to disagree. Either there's a systematic error in one or both measurements that produces a consistent bias, or the underlying cosmological model that connects the early universe to the late universe is incomplete. Those are essentially the only two options, and neither one is trivial. Let's think about why this level of disagreement matters so much for cosmology specifically. The lambda CDM model, the standard model of cosmology, has been one of the most successful theoretical frameworks in the history of science. It describes a universe that began with the Big Bang 13.8 billion years ago, expanded and cooled over time, and is dominated by dark energy and dark matter, with ordinary matter making up only a small fraction of the total. This model can explain an astonishing range of observations. It accurately predicts the detailed pattern of temperature fluctuations in the cosmic microwave background. It explains the distribution of galaxies across the universe. It accounts for the abundance of light elements like hydrogen, helium, and lithium that were produced in the first few minutes after the Big Bang. It explains how the universe transitioned from a nearly uniform state to the complex cosmic web of galaxies and voids we see today. It successfully incorporated the discovery that the expansion of the universe is accelerating, revealed by observations of distant Type 1a supernovae in 1998, a discovery that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. The cosmological constant that gives the model its name was added precisely to account for this acceleration, and the resulting framework fits the data remarkably well. The lambda CDM model works. It works extraordinarily well. It passes test after test after test. If it were a student in school, it would be getting perfect marks on nearly every exam, except one, the Hubble constant. On this one question, the model gives an answer that doesn't match what we observe when we look at the nearby universe directly. And that single failing, that one discrepancy, is enough to keep cosmologists up at night. Because in science, a model that works almost perfectly but fails on one specific prediction isn't just almost right. It might be fundamentally incomplete. The history of physics is littered with models that worked beautifully across a wide range of conditions but broke down in specific circumstances, and those breakdowns led to entirely new theories. Newtonian gravity worked perfectly for over 2 centuries, explaining planetary orbits, tides, and projectile motion with extraordinary precision, but it couldn't explain the tiny anomaly in Mercury's orbit, a discrepancy so small that it accumulated to just 43 arcseconds per century. That one failure led to general relativity, which didn't just fix Mercury's orbit, but completely revolutionized our understanding of space, time, and gravity. Classical physics explained almost everything about light, heat, and motion, but it couldn't explain why hot objects radiate energy the way they do, producing what was called the ultraviolet catastrophe. That one failure led to quantum mechanics, which didn't just solve the radiation problem, but revealed an entirely new layer of reality at the subatomic level. The Hubble tension might be a similar kind of crack, a small specific failure of an otherwise magnificent model that's pointing towards something genuinely new. Or it might not. It might turn out to be an error that gets resolved when someone finds the mistake. But the pattern is familiar to anyone who knows the history of physics. When a precise, persistent, well-measured discrepancy refuses to go away, it often means something important is hiding behind it. Now, you might wonder whether anyone has tried to resolve this tension by simply taking an average of the two values. Just split the difference and call it 70, right? That would be tempting, but it would be scientifically meaningless. You can't average two measurements that disagree when both claim to be accurate. Averaging only makes sense when the disagreement is consistent with statistical noise, when the measurements could plausibly be measuring the same thing but getting slightly different answers due to random error. That's not the case here. The error bars don't overlap. The measurements are systematically different, not randomly scattered around a common value. Taking an average would mask the problem rather than solving it. It would give you a number that neither measurement actually supports and that no cosmological model predicts. The tension exists because the two numbers are different, and in understanding why they're different is far more important than papering over the gap with arithmetic. Over the past few years, several major developments have made the tension harder to dismiss. One of the most important came from the James Webb Space Telescope, launched in December 2021. One of the concerns about the distance ladder measurement had always been the possibility that the Hubble Space Telescope's observations of Cepheid variable stars in distant galaxies might be affected by crowding. When you observe a galaxy tens of millions of light years away, even with a powerful telescope, individual stars are hard to resolve. They can blend together. A Cepheid might appear brighter than it actually is because its light is blended with unresolved stars nearby. If Cepheids are systematically measured as brighter than they really are, the distances to their host galaxies would be underestimated, and the Hubble constant would be overestimated. This was a legitimate concern, and it was one of the most commonly cited potential systematic errors in the distance ladder approach. The James Webb Space Telescope was perfectly suited to test this possibility. Its infrared instruments have significantly higher resolution than the Hubble Space Telescope, meaning it can separate individual stars more cleanly in distant galaxies. In 2024, the SH0ES team published results using James Webb observations of Cepheids in several galaxies that had also been observed by Hubble. The result was clear. The Cepheid measurements from James Webb were consistent with those from Hubble. The crowding effect was real but small, and the Hubble Space Telescope observations had already accounted for it adequately. The distance ladder result didn't change. The Hubble constant from the distance ladder was still about 73. The James Webb Space Telescope didn't resolve the tension. It confirmed it. It took one of the most plausible sources of systematic error off the table, making the tension more robust rather than less. Meanwhile, other independent methods have been weighing in. One particularly important alternative approach uses gravitational lensing. When light from a distant quasar passes near a massive galaxy on its way to Earth, the galaxy's gravity bends and distorts the light, creating multiple images of the quasar. These images don't all arrive at the same time because the light in each image follows a slightly different path, traveling a slightly different distance through space. The time delay between the images depends on the distances involved, which depend on the Hubble constant. By measuring these time delays carefully, astronomers can estimate the Hubble constant without relying on Cepheids or supernovae at all. It's a completely independent method. The H0L ICOW collaboration and its successor, TDCOSMO, have used this technique on multiple lensed quasar systems. Their results cluster around 73 to 74, consistent with the distance ladder and inconsistent with the CMB prediction. This is significant because it means the disagreement isn't just between one method and the CMB. Multiple independent late universe methods are pointing toward a higher value. Another approach uses the tip of the red giant branch as a distance indicator instead of Cepheids. Red giant stars reach a maximum brightness at a specific stage of their evolution when helium fusion ignites in their cores. This maximum brightness is roughly the same for all red giants of a given chemical composition, making it a useful standard candle. The Chicago Carnegie Hubble program, led by astronomer Wendy Friedman, has used this method to measure distances to nearby galaxies. Their early results gave Hubble constant values that seemed to fall between the CMB and distance ladder results, around 69 to 70, which generated significant excitement because it suggested the tension might be less severe than thought. However, more recent analyses and reanalyses of the tip of the red giant branch data have produced results that span a range, with some analyses finding values closer to 70 and others finding values closer to 72 or 73. The method is powerful but still being refined, and different calibrations of the technique give somewhat different answers. The situation remains unsettled, and the tip of the red giant branch hasn't clearly resolved the tension. Yet another independent approach uses surface brightness fluctuations. When you look at an elliptical galaxy, its surface isn't perfectly smooth. There are tiny variations in brightness caused by the fact that the galaxy is made of individual stars. The amount of this graininess depends on the distance. A nearby galaxy looks grainier because its individual stars are better resolved. A distant galaxy looks smoother because the stars blur together more. By measuring this graininess precisely, you can estimate the distance. Results from this method have also tended to favor a higher Hubble constant, around 70 to 73, though with larger uncertainties than the Cepheid-based approach. Then, there are baryon acoustic oscillations, which provide yet another way to probe the expansion history. In the early universe, sound waves traveling through the dense plasma created a characteristic scale, a preferred separation distance between regions of higher density. This scale, about 500 million light-years in today's universe, is imprinted in the distribution of galaxies. By measuring this scale at different epochs, astronomers can trace the expansion history. Results from the Dark Energy Spectroscopic Instrument, known as DESI, released in 2024, have added new information to this picture. DESI's measurements of baryon acoustic oscillations at multiple redshifts hint at interesting behavior in the expansion history, including possible evidence that dark energy might not be perfectly constant over time. If dark energy varies, this could affect the relationship between the early universe and late universe measurements, potentially helping to explain the tension. But these results are preliminary and their interpretation is still being debated. The picture from baryon acoustic oscillations is evolving rapidly and hasn't yet delivered a clear verdict. What's striking about all of this is the pattern. Multiple independent methods using completely different physics, different objects, different observations, different analysis techniques produce Hubble constant values that cluster into two groups. The early universe methods, primarily the CMB, give about 67 to 68. The late universe methods, including Cepheids plus supernovae, gravitational lensing time delays, and surface brightness fluctuations, tend to give about 70 to 74. The split isn't between one method and all the others. It's between early universe and late universe approaches, between looking at the universe as it was and looking at the universe as it is. This pattern is suggestive. It implies that the issue might not be with any one particular measurement technique, but with the connection between the early universe and the late universe. Something might be happening in the intervening 13 billion years that our model doesn't account for. Now, I want to be very clear about something. The Hubble tension is real, the measurements are rigorous, the disagreement is statistically significant, but this doesn't mean that all of cosmology is broken. The lambda CDM model still works extraordinarily well for the vast majority of observations. The cosmic microwave background is still beautifully explained by the model. The large-scale distribution of galaxies still matches the predictions. The abundance of light elements still checks out. The evidence for dark matter and dark energy is still strong. The age of the universe is still about 13.8 billion years, give or take a few 100 million depending on which Hubble constant you use. The Hubble tension is a crack in the foundation, but the building is still standing. It's not a demolition order. It's a warning that something in the basement needs attention. This is an important distinction because in popular media, scientific tensions and anomalies often get exaggerated. A headline that says, "Cosmology is in crisis," sells more clicks than one that says, "Precise measurements show a persistent but not yet understood discrepancy in one cosmological parameter." But the second headline is more accurate. The tension is significant and potentially revolutionary, but it hasn't overturned cosmology. It's challenged one specific aspect of the standard model, and that challenge needs to be resolved. But the resolution might turn out to be something relatively modest, a refinement of our models rather than a wholesale replacement. Think of it this way. If you're building a house and you find that one wall doesn't quite line up with the rest of the structure, you don't tear the whole house down. You investigate why that wall is off. Maybe the foundation shifted slightly. Maybe the measurements were slightly wrong. Maybe the building materials behaved differently than expected. You find the issue and you fix it. The rest of the house is fine. The Hubble tension is like that misaligned wall. Something isn't fitting together the way it should. But the rest of the structure, the rest of cosmology, is solid. That said, the resolution of the tension could be genuinely transformative. If it turns out that new physics is required, that could open doors we don't even know exist yet. It wouldn't demolish the existing framework, but it might extend it in surprising and profound ways. General relativity didn't demolish Newtonian mechanics. It extended it. Quantum mechanics didn't demolish classical physics. It revealed a deeper layer beneath it. The resolution of the Hubble tension might similarly reveal something new about the universe that builds on what we already know rather than replacing it. One of the most important things to understand about the Hubble tension is what it's not. It's not a debate between believers and skeptics. It's not a case of one group of scientists denying reality and another group defending truth. Both sides of this tension are populated by brilliant, careful, honest researchers who are all trying to get the right answer. The SH0ES team measuring the distance ladder and the Planck team measuring the CMB are not enemies. They're colleagues working on different aspects of the same puzzle. They go to the same conferences, they read each other's papers, they challenge each other rigorously but respectfully. Science thrives on this kind of productive disagreement. It's also not a case where one measurement is obviously superior to the other. Both the distance ladder and the CMB approaches have been subjected to extraordinary scrutiny. Both have withstood that scrutiny. Both have been confirmed by independent groups using independent data. If there's a systematic error hiding in one of them, it's an error that has resisted detection by some of the smartest people in the world using the most sophisticated instruments ever built. That doesn't mean such an error can't exist. Systematic errors, by their nature, are the ones you don't know about. They hide in assumptions, in calibration procedures, in analysis choices that seem perfectly reasonable but might be subtly wrong. But the fact that the error, if it exists, has survived decades of searching is itself informative. It means the error, if it's there, is subtle and deep, not obvious and shallow. It's also worth appreciating what the tension has already accomplished, regardless of how it's ultimately resolved. It has driven extraordinary improvements in measurement precision. The quest to resolve the tension has pushed astronomers to refine every rung of the distance ladder, to cross-check every assumption, to develop new independent methods for measuring cosmic distances. The James Webb Space Telescope observations of Cepheids were motivated in large part by the desire to test the distance ladder against the Hubble tension. The H0 Likau gravitational lensing program was specifically designed to provide an independent check on the Hubble constant. The DESI survey's baryon acoustic oscillation measurements are being analyzed with the Hubble tension explicitly in mind. The tension has focused the attention of the cosmological community on a specific quantitative question in a way that has accelerated progress across multiple fronts. The tension has also reminded cosmologists of something they already knew but sometimes forgot, that the lambda CDM model, despite its spectacular success, is a model. It's a mathematical description of the universe that fits the data we have. It's not the universe itself. Models can be incomplete even when they're incredibly successful. They can work beautifully across a wide range of conditions and still miss something important. The history of physics teaches us that no model is ever final. There's always a deeper level, a more complete description waiting to be discovered. The Hubble tension might be pointing us toward that next level. As of right now, in the mid-2020s, the Hubble tension remains unresolved. Despite decades of refinement on both sides, despite new telescopes and new techniques and new independent methods, the gap persists. The measurements keep getting more precise, and the disagreement keeps refusing to disappear. This is both frustrating and exciting in equal measure. Frustrating because we want answers, and the universe isn't giving them to us easily. Exciting because a problem that resists easy solutions is usually a problem worth solving. The tension has survived every attempt to explain it away. It has outlasted predictions that it would dissolve with better data. It has shrugged off dozens of proposed systematic errors that turned out not to be large enough to matter. Whatever is causing this discrepancy, it's not something trivial. And that persistence raises an obvious question. If the measurements are both correct, then what needs to change in our understanding of the universe to make them agree? What might we be missing? The possible answers to that question range from the modest to the revolutionary, and that's where we need to go next. What's remarkable is how much can hinge on such a small number 5 to 6 kilometers per second per megaparsec. In human terms, that's nothing. It's a tiny velocity spread over an enormous distance. But in cosmological terms, it's everything. It's the difference between a universe that matches our predictions and one that doesn't. It's the difference between a model that's complete and one that's missing something. It's potentially the difference between the physics we know and physics we haven't yet imagined. The universe is 13.8 billion years old, 93 billion light years across, filled with trillions of galaxies and countless stars. And one small number, one persistent disagreement between two measurements of how fast all of it is expanding, might be the key that unlocks the next great revolution in our understanding of reality. The tension is small, its implications could be enormous. So, if the Hubble tension is real, if it's not just a statistical fluke and not just an undetected error in someone's data, then what's causing it? What could possibly make two extraordinarily precise measurements of the same universe produce different answers? This is the question that keeps cosmologists awake at night, and the possible answers range from the disappointingly mundane to the genuinely revolutionary. Let's walk through them carefully, because understanding what might be wrong is just as important as understanding what we already know. The first and most conservative possibility is that one or both measurements have a systematic error that nobody has found yet. This might sound unlikely given how thoroughly both approaches have been scrutinized, but systematic errors are sneaky. They're not random mistakes that average out with more data. They're consistent biases built into the measurement process itself, and they can persist for decades without being detected. The history of science is full of examples. For years, neutrino experiments at the Opera detector appeared to show neutrinos traveling faster than light. The result was eventually traced to a loose fiber optic cable. The error was real, it was systematic, and it wasn't obvious until someone specifically looked for it. In the case of the distance ladder, there are several places where systematic errors could potentially hide. The Cepheid period luminosity relationship, which is the critical second rung of the ladder, depends on calibration. The intrinsic brightness of a Cepheid with a given period depends somewhat on the star's chemical composition, specifically its metallicity, the abundance of elements heavier than hydrogen and helium. Cepheids with higher metallicity are slightly different from Cepheids with lower metallicity. If the metallicity correction isn't applied perfectly, distances could be systematically off. Teams have studied this effect extensively and believe they've accounted for it. But the correction involves assumptions about the stellar physics of pulsating stars, and those assumptions might not be exactly right. There's also the question of dust. Interstellar dust absorbs and scatters light, making distant objects appear dimmer and redder than they actually are. Astronomers correct for this using observations at multiple wavelengths, since dust affects shorter wavelengths more than longer ones. But the properties of dust, the size of the grains, their composition, their distribution along the line of sight, vary from one region of space to another. If the dust correction is systematically wrong, even by a small amount, it could bias the distance measurements and shift the Hubble constant. Observing in infrared light, as the James Webb Space Telescope does, reduces the dust problem significantly because infrared light is much less affected by dust than visible light. The fact that James Webb's Cepheid measurements agree with Hubble's is reassuring on this front, but it doesn't completely eliminate the possibility of subtle, dust-related errors. The type 1. A supernova standardization is another potential source of concern. These supernovae are not all identical. They vary in their peak brightness, their color, and the shape of their light curves. Astronomers use empirical relationships to standardize them, correcting for these variations to determine a consistent intrinsic brightness. But these empirical relationships are derived from the data itself, and there's always a risk that they don't fully capture the true variation. Some studies have suggested that supernovae in different environments, in galaxies with different star formation histories or different chemical compositions, might behave slightly differently even after standardization. If the supernovae used to measure the Hubble constant are systematically different from those used to calibrate the method, the result could be biased. On the CMB side, systematic errors are also possible, but harder to envision. The Planck satellite's measurement of the CMB is extraordinarily clean. The data has been analyzed by multiple independent groups using different analysis pipelines, and they all get consistent results. The potential for instrumental systematics has been thoroughly investigated. The main vulnerability on the CMB side isn't in the data itself, but in the model used to interpret it. The Planck team doesn't directly measure the Hubble constant. They measure the pattern of temperature fluctuations in the CMB and then use the lambda CDM model to infer cosmological parameters, including the Hubble constant. If the model is wrong, the inferred value could be wrong even if the data is perfect. This is a subtle but crucial point. The CMB measurement of the Hubble constant is model dependent. It assumes that the lambda CDM model correctly describes the physics of the universe from 380,000 years after the Big Bang to the present day. If something happened during those 13.8 billion years that the model doesn't account for, the predicted Hubble constant could be off, the data would still be correct, the model would be incomplete. So systematic errors remain possible on both sides, and the search for them continues. But as years pass and teams keep looking without finding the smoking gun, the possibility that this is just a measurement problem becomes less and less satisfying. The error, if it exists, would have to be subtle enough to have evaded detection by dozens of independent analyses, consistent enough to affect multiple independent measurement techniques in the same direction, and specific enough to produce a disagreement of exactly the right magnitude. That's a lot to ask of a hidden systematic error. It's not impossible, but it's becoming increasingly implausible. Which brings us to the more exciting possibility. New physics? Maybe the measurements are both right, and it's the model connecting them that's incomplete. Maybe something is happening in the universe that the lambda C DM model doesn't account for. Maybe there's a missing ingredient in our cosmological recipe. Something that affects how the universe expands in a way that shifts the predicted Hubble constant upward from 67 to match the observed 73. This is where things get genuinely interesting, because the proposals for new physics are creative, varied, and in some cases, profoundly weird. One of the most discussed proposals is called early dark energy. The idea is that in addition to the dark energy we already know about, the dark energy that's driving the current accelerating expansion of the universe, there might have been a brief episode of extra dark energy in the early universe. This early dark energy would have been present for a short period around the time of recombination, when the CMB was released, and then quickly decayed away, leaving no direct trace in today's universe. What would early dark energy do? It would cause the universe to expand slightly faster during that brief period. This faster expansion would change the size of the sound horizon, the characteristic scale imprinted in the CMB by acoustic waves in the early universe. The sound horizon is a critical ruler that the CMB uses to determine distances, and, through them, the Hubble constant. If the sound horizon was actually smaller than the lambda CDM model predicts, because early dark energy made the universe expand faster and gave the sound waves less time to travel before recombination, then the CMB analysis would infer a higher Hubble constant. The predicted value would shift upward from 67 towards 73, potentially resolving the tension. Early dark energy models have attracted significant attention because they can, in principle, reduce the Hubble tension while preserving most of the successes of the lambda CDM model. The extra dark energy component is only present briefly and decays away, so it doesn't disrupt the late universe observations that lambda CDM explains so well. But there are problems. When you add early dark energy to the model and fit it to the full range of CMB data, the fit gets worse in subtle ways. The model can match the Hubble constant better, but it starts to struggle with other features of the CMB power spectrum. There are small but noticeable discrepancies in the heights and positions of certain peaks. The overall quality of the fit deteriorates compared to standard lambda CDM. This doesn't rule out early dark energy, but it suggests that simply adding one extra ingredient might not be enough. The model might need more careful tuning, or the idea might need to be modified in ways we haven't yet figured out. Another class of proposals involves modifications to dark matter. In the standard model, dark matter is cold and collisionless. It doesn't interact with ordinary matter or with light, except through gravity. It doesn't interact with itself. It just sits there, providing gravitational scaffolding for the universe's structure. But what if dark matter has properties we haven't accounted for? What if it can interact with itself or with other particles in ways that affect the expansion history? One idea is that dark matter might decay over time. If dark matter particles slowly transform into lighter particles plus radiation, the effective amount of matter in the universe decreases over time, while the amount of radiation increases. This shifts the balance of the universe's energy budget in ways that can affect the expansion rate. Depending on when the decay happens and how much energy is released, this could potentially help resolve the Hubble tension. Another idea is that dark matter might interact with dark radiation, a hypothetical form of radiation that doesn't couple to ordinary matter or light, but does affect the expansion rate through its energy density. These models can change the expansion history in ways that shift the predicted Hubble constant. The challenge with dark matter modifications is similar to the challenge with early dark energy. You can construct models that help with the Hubble tension, but they often create new problems elsewhere. Adding extra dark radiation, for example, changes the predicted pattern of the CMB in ways that can conflict with the Planck data. Decaying dark matter affects the growth of structure in the universe, potentially producing predictions for galaxy clustering that disagree with observations. Every time you tweak one part of the model to fix the Hubble tension, other parts start to strain. It's like trying to smooth out a wrinkle in a fitted sheet. You press it down in one place and it pops up in another. Some proposals go even further and suggest modifications to gravity itself. General relativity, Einstein's theory of gravity, is the foundation of modern cosmology. The lambda CDM model is built on general relativity. Every prediction it makes about the expansion of the universe, the growth of structure, the behavior of the CMB, all of it flows from Einstein's equations. But what if general relativity isn't quite right on cosmological scales? What if gravity behaves slightly differently over vast distances or at certain epochs in cosmic history? Modified gravity theories have been around for decades, proposed for various reasons, including the desire to explain dark energy without invoking a cosmological constant. Some of these theories predict subtle differences in the expansion history that could affect the Hubble constant. For example, if gravity was slightly stronger in the early universe than it is today, the expansion rate at the time of the CMB would have been different, and the inferred Hubble constant would shift. Alternatively, if the relationship between the expansion rate and the distribution of matter is different from what general relativity predicts, the way we interpret both the CMB and the distance ladder could change. But modifying gravity is extraordinarily difficult to do in a way that's consistent with all existing observations. General relativity has been tested to remarkable precision in many different contexts. From the orbits of planets, to the bending of light around galaxies, to the detection of gravitational waves from merging black holes. Any modification has to agree with all these tests, while also changing the cosmological predictions in just the right way to resolve the Hubble tension. That's a very tight constraint, and most modified gravity theories struggle to meet it. There's also the possibility that the resolution involves something we haven't thought of yet. That might sound like a non answer, but it's historically very common. When anomalies arise in physics, the eventual explanation often turns out to be something that nobody predicted. The discovery of the expanding universe itself wasn't predicted. The existence of dark energy wasn't predicted. The cosmic microwave background was predicted, but was discovered accidentally by people who weren't looking for it. Physics has a long history of surprising us. The solution to the Hubble tension might involve a physical mechanism or a property of the universe that we haven't yet conceived of. There might be an entirely new component of the universe that we haven't detected yet. There might be a property of space-time that only manifests on cosmological scales. There might be a connection between dark matter and dark energy that our current models don't capture. The possibilities are limited only by our imagination and by the requirement that any new physics must be consistent with everything else we've observed. Some researchers have explored more exotic possibilities. What if the universe isn't as homogeneous as we assume? The lambda CDM model treats the universe as uniform on large scales, meaning that on average, every large region of space looks like every other large region. This is called the cosmological principle, and it's supported by observations of the CMB, which is nearly uniform across the sky. But what if we happen to live in a region of the universe that's slightly less dense than average? A local underdensity, sometimes called a local void, would cause the universe to expand slightly faster in our neighborhood than the global average. Local measurements of the Hubble constant would then give a higher value than the global average predicted by the CMB. This idea has been studied carefully. We do appear to live in a region of below average density, sometimes called the KBC void, which extends for several hundred million light years around us. But most analyses suggest that this local underdensity isn't large enough or deep enough to fully explain the Hubble tension. It might contribute a small amount, shifting the local expansion rate up by a kilometer or two per second per megaparsec, but it's unlikely to account for the full 5 to 6 point gap. And it would be a remarkable coincidence if we happened to live in exactly the right kind of void to produce exactly this discrepancy. Another intriguing possibility involves the physics of the very early universe, before the CMB was released. The pattern of fluctuations in the CMB depends on the initial conditions set up by cosmic inflation, the brief period of extremely rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. The simplest models of inflation predict a specific type of initial conditions, and these are what the lambda CDM model assumes. But if inflation was more complicated than the simplest models suggest, if it produced initial conditions that were slightly different in ways we haven't accounted for, the CMB analysis could be subtly off. This could shift the inferred value of the Hubble constant without requiring any changes to the late universe physics. Exploring this possibility requires a very detailed knowledge of inflationary physics, which is still an active area of theoretical research. It's important to emphasize that none of these proposals has been confirmed. Each one can be written down mathematically, explored theoretically, and compared to data. Each one can partially alleviate the Hubble tension under certain assumptions. But none of them resolves the tension completely and cleanly while remaining fully consistent with all other observations. Every proposed solution creates some tension of its own, either with the CMB data, or with measurements of cosmic structure, or with other cosmological observations. The Hubble tension is proving remarkably resistant to simple fixes. It's not a problem that yields easily to a single clever idea. This resistance is actually informative. It tells us that whatever is causing the tension is not a small, isolated effect that can be patched with a minor adjustment. It seems to involve something more fundamental about how the universe works. The fact that so many smart people have tried so many different approaches and none of them has definitively solved the problem. suggests that the answer, when it comes, might be surprising. It might involve physics that we're not yet considering, or connections between phenomena that we haven't yet recognized. So, what happens next? Where does the field go from here? The answer is more data, better data, different data. Science ultimately resolves its disputes through observation, and a wave of new experiments is coming that will bear directly on the Hubble tension. On the distance ladder side, the James Webb Space Telescope will continue to observe Cepheids in more galaxies, extending the reach and precision of the calibration. Future observations will extend the Cepheid measurements to new host galaxies, improving the statistics and reducing the potential for sample-specific biases. New surveys will discover thousands more Type 1a supernovae, providing a much larger and more diverse sample for measuring the expansion rate at various distances. On the CMB side, new experiments are coming that will provide independent measurements with different instruments and different systematic properties. The Simons Observatory, now beginning operations in Chile's Atacama Desert, will measure the CMB with greater sensitivity and finer angular resolution than Planck in certain frequency bands. CMB-S4, a next-generation ground-based experiment planned for later this decade, will be even more powerful. These experiments won't just confirm or challenge Planck's results, they'll measure additional properties of the CMB, including its polarization, with unprecedented precision. These additional measurements will provide new constraints on cosmological parameters, potentially breaking degeneracies that currently limit our ability to distinguish between different theoretical models. Gravitational wave astronomy is opening yet another independent window on the Hubble constant. When two neutron stars merge, they produce both gravitational waves and electromagnetic radiation. The gravitational wave signal tells you the distance to the merger directly, without relying on any rung of the cosmic distance ladder. The electromagnetic signal, if you can identify the host galaxy, gives you the redshift. Combining the two gives you a measurement of the Hubble constant that's completely independent of both the distance ladder and the CMB. The first such measurement came from the neutron star merger GW170817, detected in 2017. The result was consistent with both the distance ladder and the CMB values, but with large uncertainties. As more neutron star mergers are detected over the coming years, the precision of this method will improve dramatically. It might eventually provide a definitive tiebreaker between the two competing values. DSE, which I mentioned earlier for its preliminary baryon acoustic oscillation results, is continuing to collect data at a rapid pace. Each new observing season adds galaxies by the millions to its three-dimensional map. Within a few years, the statistical power of the survey will increase dramatically, and the tantalizing hints it has already provided will either sharpen into firm conclusions or fade into statistical noise. If the expansion history genuinely deviates from the lambda CDM prediction at multiple epochs, DESI will be the experiment most likely to pin down exactly when and how that deviation occurs. The Vera C. Rubin Observatory, expected to begin its primary survey soon, will monitor billions of galaxies over a decade, discovering millions of transient events, including thousands of Type 1a supernovae. This flood of supernova data will transform the statistics of the distance ladder at its highest rungs, providing much more precise measurements of the expansion rate at various distances. The Rubin Observatory will also measure gravitational lensing by large-scale structure, which provides independent constraints on the growth of cosmic structure and the distribution of matter in the universe. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting a survey of the shapes and positions of billions of galaxies over a large fraction of the sky. Euclid's measurements of gravitational lensing and galaxy clustering will provide precise constraints on dark energy and the growth of structure, complementing the CMB and distance ladder approaches. Together with DESI and Rubin, Euclid will provide an unprecedented map of how the universe expanded and how structure grew over the past 10 billion years. All of these experiments are converging on the same set of questions. Is the expansion rate of the nearby universe genuinely different from what the early universe predicts? If so, when did the deviation begin? What physical mechanism is responsible? Is it something that affects the expansion rate directly, or does it change the conditions in the early universe that determine the predicted value? The next decade of observations will produce a dramatic improvement in our ability to answer these questions. We may see the tension sharpen to the point where new physics becomes undeniable, or we may see it resolve as new data reveals a previously undetected systematic error. Either outcome would be a major advance in our understanding of the universe. But let me step back for a moment and think about what the Hubble tension means beyond the technical details. Because at its core, this story is about something deeply human. It's about our desire to understand the universe we live in and our willingness to follow the evidence wherever it leads, even when it leads somewhere uncomfortable. For decades, cosmologists have been building a model of the universe that works spectacularly well. They've tested it against observations, and it's passed nearly every test. They've used it to make predictions, and those predictions have been confirmed. The Lambda CDM model has given us a coherent, consistent, well-supported picture of a universe that began in a hot, dense state 13.8 billion years ago, and has been expanding and cooling ever since. This picture has been one of the great intellectual achievements of human civilization. We should be proud of it, but we should also be humble about it. Because the universe is under no obligation to be simple enough for us to understand completely with the tools we have today. The Hubble tension reminds us that our models are approximations. They capture much of reality, perhaps most of it, but not all of it. There are aspects of the universe that we haven't figured out yet, phenomena that our models don't describe, physics that we haven't discovered. And that's okay. That's how science works. Every generation builds on the work of previous generations, extending our understanding a little further, seeing a little more clearly. The Hubble tension isn't a failure of science. It's science, working exactly as it should. A measurement disagrees with a prediction. Scientists investigate. They test hypotheses. They build new instruments. They collect more data. And eventually they figure out what's going on. That process might take years or decades. It might require ideas that no one has had yet, but it will produce a better understanding of the universe, a deeper and more complete picture of reality. The universe is expanding. We know that. It's been expanding since the Big Bang, carrying galaxies apart, stretching space itself, cooling and evolving over billions of years. The Hubble constant tells us how fast this expansion is happening, and through that single number, it connects us to the age of the universe, its size, its composition, and its ultimate fate. Two methods measure this number. One looks at the nearby universe and finds 73. The other looks at the distant past and predicts 67. Both methods are rigorous, both are precise, and they disagree. This disagreement might turn out to be a measurement problem that gets resolved when someone finds the error. It has happened before. It will happen again. Science is full of disagreements that dissolve when the data gets better or the analysis gets more careful. But the Hubble tension has survived an extraordinary amount of scrutiny. It has persisted through improvements in instruments, methods, and analysis that would have killed a lesser discrepancy. It refuses to go away. And that persistence is what makes it exciting. Because persistent, well-measured disagreements between theory and observation are the raw material of scientific revolution. They're the cracks in the foundation that reveal hidden rooms below. Time and again, the universe has hidden its deepest secrets inside small inconsistencies. A slight wobble in a planet's path. A faint glow of microwave radiation that wouldn't go away. Distant supernovae that were dimmer than they should have been. Each of these seemed like a minor puzzle at first. Each one was dismissed by some as a measurement error or a trivial theoretical oversight. and each one turned out to be a doorway to an entirely new understanding of reality. The Hubble tension might be another such doorway, or it might not. We won't know until we walk through it, but the universe is giving us a clue, a precise, quantitative, persistent clue that something in our picture of reality doesn't quite fit. The expansion rate we measure today doesn't match the expansion rate our best model predicts from the conditions of the early universe. Either our measurements are subtly wrong, or our model is subtly incomplete, or the universe is doing something we haven't thought of yet. Whatever the answer turns out to be, it will teach us something profound about the cosmos we call home. The universe is expanding faster than it should. That simple statement, that one stubborn disagreement between two numbers, might be the most important clue the universe has given us in a generation. And the story of how we resolve it, of how we follow that clue to its conclusion, whatever that conclusion turns out to be, will be one of the great scientific stories of our time. When you go outside tonight and look up at the stars, remember this: the universe is vast, ancient, and still full of mysteries. We've learned an extraordinary amount about it in just a few centuries of careful observation and creative thinking. We've mapped its structure across billions of light years. We've traced its history back to within fractions of a second after its birth. We've identified its major components and described their behavior with remarkable precision. But we haven't finished. The universe still has secrets. And one of those secrets, hidden in the gap between two numbers, between 73 and 67, might be the key to the next great chapter in our understanding of reality. The expansion of the universe is the heartbeat of the cosmos. It drives the evolution of everything, from the formation of the first atoms to the birth of stars and galaxies, to the eventual fate of all matter and energy. Understanding that heartbeat, measuring its rhythm precisely, is one of the most fundamental tasks in all of science. Right now, that rhythm has a discordant note. Two instruments are listening to the same heartbeat and hearing slightly different tempos. Resolving that discordance won't just fix a number in a textbook. It could reshape our understanding of dark energy, dark matter, the early universe, or even the nature of gravity itself. The universe is trying to tell us something. We're listening. We're building better instruments to hear more clearly. We're developing new theories to make sense of what we hear. And in the coming years, we will either find the error that explains the discrepancy, or we will discover something genuinely new about the cosmos. Either way, our understanding will deepen. Either way, the universe will become a little less mysterious and a little more wondrous, because that's what happens when science works. The mystery doesn't diminish, it transforms. It becomes knowledge, and that knowledge opens up new mysteries that we hadn't even known existed. The Hubble tension is one of those mysteries, small enough to fit in a single number, large enough to reshape cosmology, and beautiful in its stubborn refusal to go away. Whatever the universe is trying to tell us through this discrepancy, we owe it to ourselves and to the cosmos that created us, to listen carefully and follow the evidence wherever it leads. Good night. And may you never look at the expanding universe the same way again.